I'm Clara Tomasini. I'm a PhD student at the University of Zaragoza in Spain. I'm French originally, which you can probably tell from the accent I have in English. As I said, I'm a PhD student and I'm almost done. I'm finished writing the full manuscript now. So what I'm going to do today is give you a bit of an overview of the PhD, the full 5 years that I've just finished. Well, almost. Once I get back to Spain next week, I'll be done. The title of my PhD is In Understanding in Medical Images. It's quite a broad title because we didn't know where we were going first. But actually, what you'll see is medical images are mostly endoscopies, with a small and very limited so far extension to CT scans, which is what I've been doing here. I've been here for about 3 months doing a research stay as the final step of the PhD. Right. So what we aim to do is, ideally, the example that we have on the right, that's all done manually. So it's in an endoscopy scene, being able to identify the different components that we have, the semantic information that we can get. So we have different objects, the surgical tool, anatomical structures or pathological findings. So the polyp in yellow, in blue, that's a fold because that's a colonoscopy. So colon is basically a big muscle. And when it contracts, it creates folds along the surface. So that's what you have in blue. All the artifacts here, like specularities, in purple are there. That's because if we want to apply more models, then these specularities usually are bothering us to actually, so the models actually perform well. So yeah, we've been working on creating or adapting more general purpose models and developing new ones, tailoring them specifically to the medical images, the endoscopy images, and the characteristics, the different elements that we can see in these images. Some of the more challenging aspects that we focused on are first data scarcity. So basically acquiring clinical data in real practice is very expensive in terms of cost, labeling them as well. You need experts that they need time, which they don't have because time is limited. So we try to leverage other types of data, specifically simulated images and synthetic images. And another aspect that we focused on is clinical translation. So we're segmenting the example that I showed earlier, where we segment tools, we segment the folds. That's not directly useful for the clinicians, except maybe detecting polyps or tumors. But other than that, it's not directly useful. So how can we include the outputs that we get, the semantic representations that we get, into end-to-end pipelines that are actually clinically useful for doctors. So first, focusing on learning and the data constraints or having limited data. Actually, we started with contributing to having more data, making more data available. So part of the PhD, most of the PhD, was done within the EndoMapper project. That's a European project that ended last year. The idea was to be able to map the colon in real time. So as part of this project, we compiled and we released a huge data set of 4 recordings that we went to the hospital and recorded. The whole procedures are calibrated, and we added some labels. Part of them I was doing, which is tool segmentation. And what we did with these tool segmentation labels is that we tried to take existing segmentation models. So in this case, we used Mininet. It's a lightweight real-time segmentation model. that was actually developed by someone in my lab, and tried to apply it to full procedures, meaning that we take the whole video and we apply the segmentation model to all the frames. The existing methods usually focus on just the frames with the tools. That's cool, it works well, but in practice, most of the frames you don't have tools. You have very small, like maybe 200 frames, so you have actually a tool, and then you have nothing. And the images without tools, you get a lot of false positives. So what we propose to do is add a classification module that uses the same encoder from Mininet, so encoder, decoder, basic, classic segmentation framework, and we use the same encoder head to apply our classification module. And if we classify that there's no tool, we actually skip the frame and say don't apply the decoder to segment. So from that work, we were able to improve the performance on full videos and not just small individual frames. Right, but that's the ideal case when you have actual labels, enough labels to train, etc. What happens when we want to work on the task that we don't have labels for, and we would actually need proper experts to obtain these labels? We try to instead leverage synthetic or simulated data. The idea is that you take this synthetic data, try to give it a realistic approach, realistic appearance. The issue with that is that you need to find the right balance between giving it realistic texture, but actually we're also maintaining the structure of the image, because all the components of the image need to remain exactly where they are. That's what we want to segment. So if we move them, you would lose the labels that we can get automatically with synthetic data. So yeah, as I said, how can we make synthetic data images realistic enough while also enforcing some sort of anatomical structure, having a constraint on the scene structure organization. The first one we worked on was using a cycle GAN image-to-image style transfer from simulated columns. So that's what you have up there. Yeah. So we took a 3D model of the column that we got from CT scans, put it through Blender, added some sort of texture that's not really realistic, but you get colors at least that are possible. That model, because it's a 3D model and we wanted to work on segmenting the folds, that's the blue ones that I showed in the first images. That's actually when there's a curvature change in the 3D model, so that we could automatically label them, so that the labels are the white parts in the binary model. And then from these images, these simulated images that we generated, we wanted to use CycleGAN to obtain a realistic looking texture for these images. The issue is that CycleGAN is known for hallucinations. So yes, the texture was really good. It looked perfectly realistic, but all the folds were moved. So what we did to improve the structure of the images is that we added depth consistency to the loss terms in the CycleGAN training. The simulated images, we have depth ground truth, and for the realistic looking images, we used a pre-trained depth anything foundation model. It works fine for the real images. It's not perfect, but you don't need to train it, and it works fine. And by enforcing that the depth images should remain exactly the same, independently of the texture. Some of the images that we created, so what I was saying earlier, on the left first column, you have the target style that we want. It's not the image, but we want that style of real image. The second column is the original synthetic image. We want to maintain exactly the structure or almost exactly the structure that's in this image, and then different models that we use. So cyclogram, we can see that texture is perfect, really perfect. It looks like a real image, but the structure is completely wrong. You completely lose the correspondence with the branches labels. And the other models, the texture was not good at all. So we took that cyclogram, adding the depth consistency loss. The texture is not as perfect as the cyclogram, but it's still good enough for training the segmentation model on these augmented images. We get good enough results, and the structure is maintained, so we keep the labels. So that was using cyclogram, yeah, as I said. The best trade-off between texture and structure consistency was with our images. Yeah, so that was using cyclogram. And then we moved on to using diffusion. So that's the work actually of a student of mine, Angel. He's a bachelor thesis. We moved to diffusion to avoid all the structural deformation and the hallucinations, the issue with training stability. We moved to stable diffusion, adding control net, which is basically you can control the diffusion. The goal in this case was we had a data set with polyps, colonoscopy with polyps, and another, ours, the endomapper data set where we don't have polyps. What we wanted to do was take the polyps from the other data set and basically copy paste them into the endomapper data set, but still not randomly paste them into the images. We wanted to enforce some sort of anatomical possibility. We wanted them to be realistic, not just in texture, but also the position of the polyps and the shapes. Yeah. So what we did is that we used the depth again, because in colonoscopy that's basically all you have, because the colon is a tube. So the depth gives you a lot of information. We took the depth map and we used that as the supervision in the control net model to control the structure in the diffusion. And we pasted the polyps inside the depth map with the polyp aggregation module that's here, doing different rescalings depending on the shape of the polyp, depending on the type of depth map that we saw, because depending from which angle you're going, we wanted to know where the deepest point was. That has an influence on where you're going to find the polyp. You can't find it right in the middle of the deepest point in the depth map. You have to find it on the edges. We also had to smooth the polyp with the depth map. And using that, we generated the synthetic images, and we're able to train a polyp segmentation model on these synthetic images, and the results we got were quite nice. We still need to work on it to improve them in some way, but for a bachelor thesis, it looked quite promising. Building on that, what I've been doing here, which is following that same idea of a background anatomical constraint. How do we take polyp or nodules and paste them onto the reference background? In this case here, I've been working on lung CT, taking ones without nodules, ones with nodules, and trying to paste the nodules onto the healthy or CTs without nodules. In this case, instead of depth, because we're working with CT, depth doesn't really make sense. Instead of depth, we're using the lung mask as background constraint. And using the lung mask with the added nodule mask as the constraint in diffusion models. So what I'm working on right now, and what the contribution of this will be, is how we create the mask with added nodules, not the diffusion. For diffusion, I'm using state-of-the-art models. So to create the mask, I've been working on statistics-aware approaches. So basically, I've defined 4 characteristics to link the lung segmentation background to the nodule and find a distribution for each of these 4 characteristics. So the size ratio, if it's in the left or right side, which if I'm dividing the lung into a 3 by 3 by 3 grid, where in the grid the nodule or the centroid of the nodule is, and the distance from the edge of the lung. I get these distributions. That's all on a separate data speed. And then when I want to take a CT without nodule and a new nodule, paste it into the CT, to know where I want to paste it, how the zoom is going to be, I sample each of the 4 characteristics within the distributions and follow the sampled characteristics to actually paste it. And then that mask I use for diffusion. So far that's done. I'm still working on training the diffusion model because it's giving me issues to then see how it would perform. Right, moving on to the second part. As I've said, the outputs, except for the tumor segmentation, nodule segmentation, that's actually useful for diagnosis assistance. But other than that, or the fold segmentation, tool segmentation, that's not useful for clinicians. So how can we translate what the segmentations that we get to full vision-based systems that are useful? The first approach that we created is a diagnostic assistance pipeline for stenosis assessment in bronchoscopies. So moving up in endoscopy, now moving to bronchoscopy. Stenosis is the diagram that you have here on the right. It's basically the portion of the airway that's called the subglottis, which is between the vocal cords and just before the trachea. And there's a stenosis when the airway is narrower than it should be. That's a disease, and if it gets to a certain degree, you can't breathe. So you need to be able to obtain an accurate diagnosis and monitor the evolution of the condition regularly and in a stable and objective way to be able to plan the treatment. The issue with the stenosis assessment is that clinically it's usually done visually by the doctor going in and looking and estimating how much it measures. So what we see is that there's a very high variability between 2 different doctors. We actually we recorded these videos at the hospitals and with 2 or 3 different doctors going in, one behind the other. So back to back. So the degree of stenosis hadn't changed at all. And we should have gotten the same estimations from all 3 or 4 experts, but we didn't. We do see quite a significant variation. So what we propose is to automatically estimate it. We use segmentation and tracking to know when we're getting to the actual narrowest point of the stenosis of the airway, the red part in the diagram. And at that point, that's what we call the keyframe. That's the best position to measure the stenosis. And at that point, we use depth estimation to reconstruct the 3D model of the airway. In this case, the depth model is one that was also part of the NUAPA project. We reconstruct a 3D model of the airway at that point, and then with planes and intersecting that model, we can measure the obstruction. So I have an example of how it runs on a real video. That's at the point of the stenosis that's very narrow, and we reconstruct the model, reconstruct the airway, and then we get the planes. The green one is the stenosis, the blue one looks great. It's actually the healthy size, the size it should be if there wasn't stenosis in the airway. And so by doing the ratio between the green and the blue, we get the degree of obstruction of stenosis, and we know how bad it is and how much the patient can breathe. The results that we got were really promising. We were within the same ranges as the doctors, and we also show consistency because we got 3 experts to do the same procedure on the same patient, so repeated videos for same patient at the same stage of disease. In using our approach, the measurements were consistent, and we were also always within the same range as opposed to the experts. Right, and the final example I have of full-on pipeline is navigation guidance also in bronchoscopies. So basically, bronchoscopy, you take a camera, put it down the nose, trachea, and go into the airway. The airway, you have a bronchial tree structure. That's the model that's here on the right. You can't really see it, but yeah, that's up there. We got from CT and we reconstruct. Basically, it's quite complex. It has a tree structure with a lot of ramifications, and usually when doctors try to navigate through it, if they need to reach a specific point, or if they need to actually identify branches where they detect objects of interest, they have to visually remember where they are. So it's difficult as is with just knowing the structure, and also keeping in mind that the examples of bronchoscopy here at the bottom, they're really clean. That's just for the paper, the perfect images. But in practice, that's very few images. The rest are all quite, you have a lot of obstructions, you have liquids because you have to keep adding anesthesia. So it's a lot of bubbles and liquids and reflections, can't really see anything. So mentally keeping track of exactly where you are is quite complicated. So what we propose is an image-based only topological scope localization, which basically topological because we use a generic representation of the bronchial tree. That's the one down there, where basically each branch has a name that is actually clinically used, and we didn't invent that. That's the one that is actually clinically used. We don't determine exactly at what point of each section we are, because the sections are quite short. We just know that we're somewhere in that specific branch. Yes. To do that, we also release the real and simulated label data, always to keeping in mind trying to contribute to releasing more and more data, because for that task there's one data set that's available and it's phantom. It's not real looking, it's just one model or one phantom. So it's as if you are doing all the experiments in the same patient, so you have no variability really. So yeah, we release I think 4 or 5 real sequences and about 9 simulated ones. An overview of the approach that we call bronchotop. So we take in the bronchoscopy feed, just the RGB video that we get in, and what we want to see at the end that would be the screen at the hospital. We want to see the label of each of the branches that are visible. That's the 2 green boxes, the 2 openings that you see at the end, and also within the tree model, knowing where the model thinks the camera is. So what we do to obtain that is we detect the lumens. The lumen is the opening, the black part. We track them, assign them a label within that tree, and then we compute probabilities of location based on the labels that we actually see tracked at that specific frame, and the ones that we were seeing earlier in time, because it's sequences, so you do have a temporal aspect. Yeah, and then we have a module to verify if the model indicates that there's been a switch in location. We have a module to verify that it is actually a switch, and from that we can update the location. An example of how it runs. Yeah, that's in simulated data, so that's the easy part. We get about 90% accuracy. You have on the right when the square is green is that the location is right, and the only thing is that we have some latency right at the switch. It also happens in real. It happens when experts label. It's not exactly clear where the limit is between the different sections. But in real, it also works quite well, keeping in mind, as I've said, that's clean, shorter sequences. But it works quite well, and we were able to do the backwards movement as well. So we have these, you can go backwards, forwards, because some approaches that exist only treat the forwards movement, but at some point you have to go back and go into the next branch. So yeah, that works quite well as well. And that's about all I have. Yeah, I want to say thank you for the attention and for having me here. Well, thank you.